So we will start geometrical optics now, and I'm going to put here geometrical optics. And what we need to consider is how light behaves when it goes through two types of lenses and when it bounces off of two types of mirrors. So let me state this here. We have two types of lenses. Here's one, here's the other one. And we have two types of mirrors. I'm gonna draw them like this. And here's the other one. Curves like this. And of course we do have a flat mirror, but I'll add it. So we have a flat mirror. So the first two are lenses. And this is specifically called, well, these two are lenses. Lenses. And the first one is called the converging lens. It converges the rays of light into its path if they come from far enough away. And then this is a diverging lens. Diverging lens, it causes the light rays to spread out, and you will see how that works out. Then we have mirrors. So all these are mirrors. Mirrors. Here's a flat one. Here's a concave mirror, and here's a convex. Sometimes I mix these two up, but I think I got this one right. Anyways, here's a concave and here's a convex mirror, assuming I didn't mix them up. So lenses are transparent. These are transparent. Transparent. And the light goes through. I'm going to put here the light goes through these lenses. And in the case of mirrors, they're not transparent, the light reflects. So I'm going to put here not transparent. Light bounces back. Light bounces back. And let's maybe see what's happening with the converging and diverging lenses first. So let's scroll this up a little. Let's consider a converging lens. So here is a lens. All of these, it's customary to draw a line of symmetry here. Goes through the middle of the lens. And let's consider some rays of light that come in from very, very, very far away. So let's say here's a ray of light. It is parallel to the center axis. It goes through the lens, and well, it's going to change the direction. Through the process called refraction, this ray of light is going to change the direction and go more or less like this. Always traveling in a straight line, and then maybe we'll do a couple more of these. So you're going to have another ray of light that goes here, parallel to the central axis. Through the process of refraction, it's going to change its direction, and it's going to go and cross right there. And let's add a few more. So let's say we have another ray of light that goes like this, and another one that goes like this, and one that goes along the central axis here. And as long as all of these are here, as long as all of these are parallel, they will all converge into one point. I'll draw this one, I'll draw this one. The one that goes along the central axis, of course, just continues on and goes straight through. Right, and so this is what we would call the focal point. This is a focal point, and this is where all of the energy of light that is coming from the left-hand side is going to be concentrated. So if you were to place a piece of paper here, potentially you could heat up this piece of paper to the point where it could actually ignite. Because the rays of light are converging into one point here, we call this lens the converging lens. So this is a converging lens. Now, you could, of course, the focal point, of course, doesn't have to be on one side. In fact, the focal point of a converging lens is on both sides of the lens. So consider a case where you have this lens, that's the same lens, it sits here, and then here's your center axis. But now the rays of light come from the right. So you have a ray of light that goes here, and another one that goes here, and another one that goes here, and you have another one that goes here, and let's say that all of them are parallel. So they all point to the left. They come from so far away that go from very far away, and they're all parallel. They will cross. They will change the direction due to the process of refraction. And so let's say that maybe what we get is something like this, and then here something like this. All right, so this one has to go through that one point, the focal point, and this one also has to go through the focal point. And let's maybe add some arrows to this whole picture, so these rays of light will continue in this direction, but they have now formed a focal point. And because all of these rays of light converge, this is also a converging lens. The point is, though, that if you draw a converging lens, then this converging lens will have two focal points. One on the right, one on the left, and so here's the focal point here, focal point here. The distance to the focal point on both sides is the same, and we label that as just letter F. Okay, so there's your converging lens. Now let's look at a diverging lens and how that differs. So for the diverging lens, let me move this up a little. We'll have something like this. The lens looks, this is the shape of the lens. Right, it's supposed to be symmetrical. About this axis here, it's supposed to be symmetrical. So keep that in mind. Anyways, here's the, I'm gonna get rid of that because I don't need these dashed lines. And here's your central axis or axis of symmetry here, this way, the horizontal one. Now let's see what happens if you have rays of light coming in at this one. So the ray of light comes in, and maybe I'll draw one here. Goes like this. It hits the surface, and it refracts, but it will refract in such a way that it will go out an angle like this. And if we spent more time on wave properties this year, you would have known precisely why is it that these rays here will diverge out, but we'll just have to live with what we have. The only thing is that I probably should have drawn it. Let me do it like that. So yeah, okay. All right, so here's the ray of light, goes this way, and then it just diverges outwards like this. I'm trying to maintain that symmetry. Yeah, about right. And then maybe I'll do, well, let's do one more. So let's say that this ray of light comes in this way, and this one also will diverge out. Maybe like this. And then let's put one more here. The ray of light comes in, and then it diverges outwards. Like, maybe I'm trying to aim for something specific, maybe like that. Okay, and now let's give the directions here. So what we have is these rays of light just go out like that. Now, for the obvious reason, we call this lens the diverging lens. This is a diverging lens. Right, that one was converging. And in this specific case, it's clear enough that there is no actual real focal point. But if you do extend these rays of light like this, so here's a ray of light that goes out like that. If you do extend this backwards like this, right? So let's make these extensions here with dashed lines. So this is not an actual ray of light here. This is just an extension. And I do the same thing with the other rays. So let's say we extend this one now from here. It goes like this, and that should do. So there's that, and then I'll do also extend this one backwards. So if I extend this one backwards, something like that, and then I extend this one backwards. These extensions, not the actual rays of light, but rather these extensions here, make sure that these are actually extensions. So let's do that. These extensions will cross. Not the rays of light, but the extensions of the rays of light backwards will cross. So there's going to be no real focal point, but there's going to be what we would refer to as a virtual focal point, right? So this is going to be a virtual focal point. There's a focal point, but it's a virtual one. If you were to place a piece of paper here, you're not really concentrating any energy of light at this specific spot. This is just a virtual focal point. So if you were to place a paper here, it wouldn't burn. Hence we call it the virtual focal point. In this specific case here on top, if you were to place a piece of paper there, this is where you have actual physical rays of light that cross, and you could set that paper on fire. Here, you couldn't set that paper on fire. Still, there's a focal point there. And of course, you could draw the same picture in reflection of the same picture where you have, this diverging lens that goes like that. You could set it up like this, where the lens does the following, and then you have these. You have the center line, and then you draw the rays of light on this side. Coming in from right, going in from right to left. So here's that, and this is going to diverge outwards like this. And then I'll do here. Let's do this one, and this goes out like that. All right. Let's just do two more. This one goes out like that, and then this one comes here, and this diverges out. Now let's give these rays direction, so they're going in this direction. If you were to extend these, then you would find out that they would cross at a specific point, just like before, but now they would cross on the other side. And so you will end up with another focal point. It's still virtual, but it would be focal point on the other side. So what you get out of this whole picture here is that if you have a diverging lens, the diverging lens will, let's draw it maybe in the middle. So here's a diverging lens. The diverging lens would have a focal point on one side and on the other side. So you would have a focal point here and a focal point here. The difference is that these would now be virtual. These are virtual focal points, and we would still label them with F. And the two F's would be the same, assuming that the lens is actually symmetrical on both sides. So the two F's would be the same. So converging lens is here, diverging lens is here. Both of them will have focal points. All right, now let's look at the mirrors. So mirrors, the first one is a convex mirror. And if I misspoke, and this is actually the other one, I mixed these up. I tend to mix these up, but anyways, here's this lens, not lens, but a mirror. So here, let's consider a mirror, and we're going to say that this is a circular mirror. So the curvature is circular. It's a section of a circle. It's not parabolic. Parabolic mirrors would actually work better with what I'm about to say, but it doesn't really matter. So here's the central axis of symmetry, and then let's say that we have rays of light that are coming in. So here's a ray of light that comes in from all the way from the left. It hits this mirror, and then what does it do? It reflects back. It does not go through because this is a mirror. So the ray of light just goes back, and let's say does something like this. All right, and let's give this thing a direction so it goes out like that. And then let's say we draw another ray of light somewhere here. Let's do one here. So it goes this way, hits the mirror, and what does it do? It reflects back, and it's going to reflect back to a specific point right there. Give it an arrow direction, and then below, let's say we have another ray of light that goes in like this, hits the mirror right here. What does it do? It reflects, but in such a way that it will go and cross that point, and we now can call that point a focal point. Let's maybe do one more somewhere here. So here's another ray of light, goes there, reflects, and it goes through the focal point out like that. And let's give it a direction. Okay, so what we have here is for the convex mirror, I put here convex mirror, we have a focal point, which is an actual real focal point. So we have a focal point here, and it's the distance from the mirror to where the focal point is. And we just label this with F. For the concave mirror, let's draw a picture here. So here's the mirror. This is the reflective surface, so the light reflects off of it. Here's the central axis. And let's draw a few rays of light and see what happens here in this case. So here's one ray. Goes in like that, hits the mirror, and what does it do? It reflects. Let's say it reflects like this. And now let's give it the direction here. So it does the following. And let's maybe draw another one here. Reflects. And maybe one more here. Reflects again, but at a different angle. And I'm trying to, let's say maybe reflect, all right. Reflects like here. And then here comes another one, goes this way, and this reflects, let's see, I'm aiming at a specific spot, yeah, something like that. Okay, and then let's give this directions. So here's this one going like that, here's this one going like this, and here's this one going like that. Now, obviously there's no real focal point here. These rays of light don't really converge into one specific spot. Now you may say, but there's a, there's a point of crossing here. So what? You have 2 rays of light crossing that spot. That's not much. You want millions, if not billions, of rays of light crossing one spot. And here's what you have in this case: all of these rays of light, all of them which are parallel, and there are many here which are parallel, when converge to that point. Now in this case, the actual rays of light don't converge to a point, but their extensions do. So if you were to run an extension here, then you would find out that these extensions do cross at a point. So this would be a focal point. It's just that this would be a virtual focal point. So I'm going to put here virtual focal point. And F would be the distance from the mirror to the focal point. Okay. So let's stop here, and in the next video we'll look at how to draw ray diagrams for lenses and mirrors.